So here we're going to look at a couple of examples in terms of applying Bayes' theorem using the Tableau approach, the tables kind of tabulation approach to easily and quickly and in a way that is less prone to making mistakes. So here we are given the 6 numbers, right, as we were able to understand early on, given P, the prior probabilities, P of S1, S2, given the credibility matrix of the consultant. And again, this consultant is a kind of a mental device for us to understand why do we have this given S1, given S2 kind of scenario, right? So the consultant's matrix is whenever S1 happened, given that S1 happened, the chance of I1 happening is this, I2 is this. And what is I1? I1 is the at the least at the fundamental basic level, we can think of it as the consultant saying S1 will happen. Saying S1 will happen. The consultant predicts that S1 will happen going forward. So if this is the case, then we end up having these scenarios as what we tried out with a numerical example just now. So over here, we see that the values on the left here, prior is given. That means in your homework exercise, exam questions and all that, this will be given. The credibility matrix, as I call it here, the how reliable is this consultant, is also given here. Yeah, and then the rest will be the calculations. So here the calculation is we get 0.3 because we multiply 0.7 by 0.4286. We split it by the credibility matrix. We split the prior probability by the credibility matrix, right? So we just multiply the row throughout, we'll get this. Now notice that the credibility matrices across I1, I2, they add up to 1. Whereas in the earlier example, mine didn't add up to 1 because we didn't tabulate the rest, right? Remember there was 1, 2, and 3, and 4, and then there was a 5 and 6, right? The 5 and 6 didn't lie in any of the I1 or I2. Perhaps we could have just tabulated an I3, but that's making it more complicated. So I ignore that column. Much like if we ignore another column here, I1, I3, I4, I5, then these numbers in the S1 row may not add up to 1. We'll see another example in a while, right? So most likely in your homework exercise exam questions, they will add up to 1. You just have to check. So if it's not adding up to 1, not that it is problematic or wrong, but there is an I something, an additional outcome, right? Where the consultant may say something else, but that part either wasn't interesting, wasn't important in the question, or not captured, not important to consider, right? So just keep in mind that typically they add up to 1. So here we then multiply, we get this, add vertically down, we get this, and then we divide through its own column sum, right? 0.3 divided by 0.4, we get 0.75, 0.1 over 0.4, 0.25, and so on. Yeah, so we get these numbers. And they readily gives us the probability of S1 happening given that I1 has happened. So right now in this example, it's all just working on numbers. There's no context to it. So how can you even think about a situation like this? If you're given such a problem, that means it's all numerical, asking you to attack Bayes' theorem on its numerical basis without any context to it. Think of it as the consultant, right? Consultant I1, I2, consultant saying S1 will happen, saying S2 will happen, and all that. Okay, and do note that the number of I's need not be the same as number of S's. So you can have 2 S's and you have I1, I2, I3, right? Like in my Dow Jones example, it can be that Dow Jones values can be plus 100 or more, or falling by 100 points or more. And then there is this part from minus 100 points to plus 100 points is like neither here nor there. That means essentially no change. So it can be S1, S2, S3, but consultant will be I1, I2. Consultant says Dow Jones will go up or it will go down. But consultant is never going to predict anything neutral. And that's fine. I1 and I3, right? Without I2. That's fine. Or you can have S1 and S2 and you have I1, I2, I3, I4. So consultant is very more precise, more refined than the state of nature. Those are all possible scenarios and nothing is wrong with a rectangular matrix of that sort. Next example. This is interesting. Now we have, you can read here the example. But what is interesting here is that we know the prior probabilities, right? P of phone and therefore P of SMS. So the votes come in voting for A and B. They can come in via phone or SMS, and of course that's some time back. It can be now via apps or via many other means. But let's just say two channels, right? So via phone, via apps and SMS, and we gather the details, and we found that 8 out of 10, all right, given that it is phone, so coming in from phone, 8 out of 10 of those phone votes voted for A. 2 out of 10 voted for B. And because there are no further contestants, finalists, there's no C or D. Yeah. And then likewise for SMS. And so you find that they add up to 1, right? They add up to 1. And that is fine. But what is more interesting is there's the I1 here is voting for finalist A. I2 is voting for finalist B. That is not saying that the consultant says phone will happen, because it sounds very strange, right? So here, it is one example where the consultant, somebody out there, the consultant is saying something, but it is not saying S1 nor S2. It is saying voting for A, voting for finalist B. Yeah, so it's the consultant saying something, the event that the vote comes in to support A or support B. So we need to be very flexible with this consultant device, right? This mental device, that it is not just restricted to, well, the vote must be for phone or must be for SMS, which is strange. It will not be the case. Yeah. So, and it's totally fine, because it is the case that the vote, right? The message on the vote supported A, supported B, and that's totally okay. And that means it is I1, I2. So this is the interesting part of it. So given all these, and as you can imagine, we can just download the data from the server and do this tabulation very easily, right? Why are we asking this question? Because here comes a vote that is, you were told that, hey, you know what, the vote from this fan voted for A. This fan voted for A, and is a great supporter for A, finalist A, not B. Question: do you think this fan voted A through phone or SMS? Let's make a bet, something like that. So, well, of course, this is quite a trivial case, but you can see why it is rather impossible, or else difficult to ask. Maybe it's awkward to ask the fan, hey, fan, did you vote through phone or SMS? Maybe it's socially awkward to do that. Maybe it's not the right opportunity to do that. And maybe this, maybe that. You can imagine why, it is just not a viable means to ask or determine that directly. So now we calculate, we need this probability. Given that the vote is to support A, I1 has happened, what's the chance that S1 has will happen? That means, what's the chance that the vote came in through phone? All right, so this is not about the time and future, even though the vote has arrived, but this is about unknown territory. So that's another interesting thing about this. It's not about predicting the future. It's about discovering the unknown that also, although has happened, is unknown to us right now, to this particular experimenter right now. And we want to find out, did this vote come in through phone or